This is a presentation that was given at NFV World Congress by Ali Kafel of Stratus Technologies.
I'm going to talk about stateful fault tolerance, which is higher than high availability. So we've heard a lot about carrier class reliability, carrier class high availability, carrier class resiliency. So how do you provide it? And that's really what my talk is about. So at Stratus, as Michael said, we've really been in business for 35 years, started really in the hardware side, but most recently we've switched to software like everybody else. So what I'm going to talk about is a software-based, fault-tolerant infrastructure that provides seamless availability, resiliency, and reliability to VNFs. So people sometimes interchangeably talk about high availability, reliability, and resiliency. And in fact, they mean different things, right? So from a carrier perspective, availability is the amount of time an equipment is in an operable state. So it's really, uptime, the total uptime. When you hear about 99.999%, that's an availability. So over a 1 year period, that's 5 minutes. So that means your system was down 5 minutes over the year, which may or may not be a big deal, depending on the application. Reliability is how long a system performs in its intended state before it fails. So, there's a mean time between failure, which is the total time in service divided by the failures. So they don't mean the same thing. And resiliency, of course, is the ability to recover quickly from failures and return to the original state. In other words, no change whatsoever in the state. So what this really means is you may have a highly available system which may not be highly reliable. For example, if you have a system that has 5 nines of availability, that means it can fail on an average 5 minutes a year. In fact, failure may happen every week for a short period of time. So you may have a highly available system, but not reliable. And it may also not be resilient, meaning that when a failure happens, the state changes of the application. For some applications, that's a big deal. For something like an HSS and an MME, you don't want that state to fail. So really, what we talk about is really stateful fault tolerance. So stateful fault tolerance means the system is highly available. It means it's highly resilient. It means it's highly reliable. So that's what we're talking about. So the difference between the two can be shown really in this graph. So when a failure happens in a high availability system, the service is out for maybe a few seconds, maybe a few minutes, maybe a few hours, depending on the system. When it comes back, the state it's at is different. At that point, a lot of bad things could have happened. So in a stateful fault-tolerant system, as you can see, when a failure happens, the applications do not even know it's happened because the environment is taking care of it, making sure that a backup system has taken over without any state change, without any downtime whatsoever. So how do you do that? How do you provide stateful fault tolerance in a VNF? There are really 3 ways to do that. One way is the old way, which is in the hardware. That's actually how Stratus started. There are pluses and minuses of each method. If you do it in hardware, years ago, that used to be a great way to do it because we hadn't come along as far in software technology as we have today. So in hardware, there are benefits, right? It's transparent, no code change. It's fast and it's simple deployment because the application doesn't really need to do anything. And of course, there's no special software, application software that you need to deploy. The problem is, with that model, this is the cons on the bottom. It's very expensive. Hardware systems are very expensive. Stratus used to charge hundreds of thousands of dollars for one server. Those days are long gone. The other problem is it's inefficient utilization because you need a 1+1 architecture, so you tend to use a lot of hardware. The other problem is that you need special hardware. You need that fault-tolerant hardware. It may be based on Intel, but it's still proprietary, and it's very rigid. So that's not a good way. Another way is to do it in the application. And really, prior to Stratus introducing this product that we have, this stateful fault-tolerant cloud solution, telcos, obviously, need reliability. You've heard about that over and over in this conference. They need reliability, availability, carrier-grade resiliency. So a lot of the good vendors have actually put it in the VNF. There are benefits to put it in the VNF. If there's no other way, that's a great way to provide telco grade. And there are also some other specific benefits. So you can do specific code based on the application. But the disadvantage of putting it in the VNF is that every application must be modified. That's a pain. That takes a lot of time. That takes a lot of energy, a lot of complexity. And there are very few people around that know. There are a lot of good engineers around, but not a lot of good engineers that know how to do fault tolerance with state protection in an application. We've talked to several vendors, and some of them have told us, actually, by adding the reliability code, they've made the application more complex and therefore less reliable. So those are the disadvantages of that approach. So we believe there's a better approach, and that's actually putting it in the software infrastructure, right? Not in the hardware, in the software infrastructure. And the benefits highly outweigh the disadvantages. So the benefits is, like on the hardware side, it's transparent, no code change. Any application can be deployed without changing the code. It's fast, simple deployment because you can take any off-the-shelf application and deploy it. No special application, no special hardware because it runs on Intel commodity hardware. Multiple levels of resiliency. This is really important. A speaker earlier this week talked about that. There's a way to do obviously, multiple levels of resiliency because not every application needs stateful fault tolerance, right? Some of them, if an instant restart is good enough, so being able to provide that multiple level of resiliency is important. And then finally, with a software infrastructure approach, you can actually increase the efficiency of the reliability because you don't have to do it a 1+1. And I'm going to talk about that. Of course, like any solution, there are some drawbacks. Higher efficiencies for some application may be challenged depending on how the application is designed. But so if it's a monolithic application, large VMs, providing that higher efficiency may be more challenging. But beyond that, there's really all the good stuff that you see on the top. So we believe the way to do it, to provide stateful, fault-tolerant software infrastructure, is there are 4 key benefits. The first is transparency, no application code change. Any VNF can be deployed. The second is what we call in software-defined availability, which means you can provide selectable levels of resiliency with complete fault management, right? I'm going to talk about that. The third is agility and simplicity, which means it fits into any KVM OpenStack environment, and it supports any VNF. And then finally, it's the efficiency of redundancy. By this method, and I'm going to show you, it really increases the efficiency of the redundancy. So let's kind of go through it. Transparency, no application code change. How have we done this? We've actually done this by actually keeping state of the virtual machine. So we have a primary host and a secondary host. It's not 1+1. There's always a secondary, but the number of secondary physical servers are a lot less than the number of primary physical servers. So I'm going to show you kind of how we do this N+K declustering. But essentially, when a VM runs in the primary host, it runs, and then when a state changes, we hold the I/O so that you always maintain globally consistent state. We hold the I/O. We update the state to the secondary at the secondary. Then when we get the confirmation, we release the I/O, we continue. When another state change happens, again, we hold the I/O, update the secondary. When it comes back, we continue. Now, this goes on until a fault happens. When a fault happens on the primary, and they do happen, what we will do is automatically switch over everything to the secondary, seamlessly as far as the application is concerned. The application doesn't even know something has happened. And at the same time, when we do that, we start a third node, because the secondary becomes the primary, and then the third host now becomes the new secondary. Now, if you notice, I have, when the secondary started, the state N is the same as the state of the primary before it went down. So this is how we maintain globally consistent state. So that's how we do the transparency, and that's one of the benefits of this architecture. The second is software-defined availability. What that means is not every application needs stateful fault tolerance. Some do. For example, an MME, mobile management entity, does. But some applications, like a web server, maybe doesn't need any special protection. And an IMS maybe needs stateful fault tolerance, but not geographically redundant. A firewall, at least maybe in the data path, maybe an instant HA is good enough, depending on the firewall itself. If it's really at the higher levels, may need higher levels of resiliency. But essentially what it means is, with this architecture, you can deploy different levels of resiliency. Now, if an application is monolithic, like you see there, it can work in the infrastructure. If it's componentized, meaning that you separate the data plane from the control plane, even better. Because what that means is you can actually deploy the control plane in a stateful fault tolerance manner and deploy the data plane, which is called fastpath, in a stateless manner, which means it is instant HA. So this really provides the right level of resiliency for each component, including in an SRIOV environment. Okay? So beyond this multiple level of resiliency, we provide this complete fault management for all applications, whether the application is deployed in a stateful fault-tolerant manner or in an HA. Fault management means you have the mechanism to detect a failure, localize it, isolate it, recover it, and then repair, return it back to its state. So that is something we do for all applications. So someone may say, well, wait a minute. Okay, I see the benefit of your solution. I can deploy a fault-tolerant system on it. I don't need to modify the VNF. But for those applications where a restart is good enough, maybe I don't need to deploy it here. I can put it somewhere else because I'm not sure what the benefit of this is. Well, the benefit is that even for those, we can provide the restart, but we can also provide the fault management, which everybody wants to know how their application is functioning. So that's benefit number 2. Let me talk about benefit number 3. I talked about agility and simplicity. This solution, if you look at a traditional OpenStack environment, it kind of looks like this, right? You've got, your virtualization layer. That's where KVM is. You've got your orchestrator and your Mano on the left, on the right. I haven't shown it. That's your OpenStack. I'll show that in a minute. And you've got your applications at the top. This works great. However, when a failure happens, the applications actually get affected. Unless, again, you either put it in the application, which we've talked about the problems with that, or you insert a virtualized resilience layer right above the virtualization layer. And that's exactly what we've done. By doing this approach, when a failure happens, the application, if you notice, doesn't even know. It's shielded from it. Everything continues to run. And the benefit of this is that you can deploy this really in any environment, in any OpenStack environment, any Linux distribution. It doesn't matter. So this really gives that agility the telcos like, which means that they can deploy it in any environment they have, any distro distribution they have, whether it's Red Hat or whomever, or they can, and they can also deploy any application that they otherwise may not deploy. So that's benefit number 3. Now, the architecture completely looks like this. This here is what I showed you in the last picture. This is now summarized. Whoops. And what you see over there is the manual. We don't provide an orchestrator. What we do provide is obviously the resilience management layer, which provides the workload management for resiliency, not for the complete infrastructure. Of course, we take advantage of OpenStack. And the benefit of this is in how we do the efficiency of redundancy. So I mentioned before that we actually have this concept of the primary doing the work, and then the secondary standing in a hot standby mode, taking state update information. So as I said, you know, when work happens on the primary, state changes, update gets sent to the secondary, confirmation comes back, the I/O is released, and this continues for all of the VMs. Now, if you notice, the primary cylinder is bigger than the secondary cylinder because the secondary does not do the same amount of work as the primary. The primary does all the work, takes the I/O, does the CPU, you know, processing, the logic of the application, and then, you know, does state management. But then, essentially, all the secondary does is it waits and gets a state update information. That's why the secondary takes very little resources, only about 6 to 10% of the primary. Now, the reason we do this is by design. It means that every VM that you see on every server has an anti-affinity secondary backup on a different server. So VMA, for example, primary running on this physical server, the secondary is running on a different server, taking 6 to 10% of the resources. B is doing the same thing, different server, C, D, and so on. And every one of these physical servers do the same. So at the end, what it looks like is the following, is that you've got a bunch of VMs on each physical server. Each VM on that physical server has a shadow secondary on a different physical server. So that way you've got the anti-affinity model. And also what we do is for each physical server, we reserve a capacity for stand-up. So if a failure were to happen, so let's say that middle server fails, what we do is we take that server out of service, and if you notice, all of the VMs that were on that server are now awoken, the secondary VMs on the other physical servers are woken up, and because we had reserved some stand-up capacity, so we don't have any loss of state and any downtime whatsoever. And then what we do next, of course, is we replace that. This is where the recovery comes in. The dead server gets taken out. A new one gets brought in from the resource pool. We bring it back up, and everybody is happy. So by doing this, by really having a secondary in a standby mode that only uses 6 to 10% of the resources, we're able to increase the utilization of every server. So this is, you know, you've all heard, I think John Donovan from AT&T has been very vocal about how the telco network is only about 45% utilized because of the 1+1 redundancy architecture. This model really increases that utilization from 45% to 73% or 87%, depending on how you design it. So if we want, for example, the stand-up to happen in a different server, so if you add a couple of more servers, then you could really increase your utilization even higher. So what this does, it's funny, Michael mentioned 37%. As I said, wow, 37%, he's spot on. So actually this model does that savings of resources, 37.5% when you use this model, rather than using, in this model, we're using 4 servers rather than using 8 servers. You're only using 5 servers in this case. Or if you use all 8, then you really increase the capacity of your utilization. So that's what the solution is. So essentially, what I've shown you is the benefit of a software infrastructure approach to provide stateful fault tolerance, transparency, no application code change, software-defined architecture, which means it's selectable, it's agile and simple, which means it fits into any environment, and efficiency of redundancy. Now, you may wonder, is this solution available? Is this all slideware? And the fact is, it's real. We actually have a POC in this room, up on this floor. POC 35 was approved a couple of weeks ago by ETSI. The sponsors include AT&T and NTT. And the name of the POC is Availability Management with Stateful Fault Tolerance. And we are showing the last demo of it at 10:50 at the break. So if you'd like to come see it, would love to show it to you and answer any questions you may have. And I think I have a few minutes for questions.
Yes, hi. Great presentation. Thank you very much.
Thank you.
I was wondering about those, when the IO...
Yeah, here we go. And say your name and
Yes,
organization.
I'm Azito Arvani. I'm Head of Innovation Partnering at Nokia Networks. Great presentation. My question was about when you get those IOs, what's the hit to performance?
Great question. So when the IO comes in, we obviously, before we acknowledge it, we want to make sure we do the update, freeze the IO, do the update to the secondary. When we get the confirmation, release the IO. So the hit to latency is about 750 microseconds. So, and one thing I should mention, by the way, the cloud solution here I'm talking about is relatively new, but the underlying technology that provides the stateful fault tolerance is not new. It is software that Stratus has deployed at 15,000 enterprises around the world, so it's really proven. It's really based on that. We've taken a lot of measurements, so it's about 750 microseconds is the latency hit.
And then the difference between fault tolerance and high availability, what's the difference?
Another great question. So right now, the worst case, so if you deploy all the applications in a stateful fault tolerant manner, which uses the most amount of resources, the difference is about 60% of the non-FT mode. Okay, that's the worst case. Now, the reality is when you have a mix, some FT, some HA, it's much higher than that.
Another question back here. And then we'll take, if we have time.
Okay.
Thank you. It's an interesting presentation. The questions, actually, my reservations are regarding the no application code change part for the redundancy. Let's just take an example of TCP. And can you just give me one sentence, say how do you actually do the TCP, which is stateful, and then doing the redundancy on it? Thank you.
Yeah, so as I mentioned, we actually protect the state of every application if it's deployed in a stateful fault tolerant option. So we will protect the state for every application in the VM. So we don't look at a specific application. That's what makes this so nice, because it's not specific to our application. As long as the application is running in a VM, we look at the dirty pages of each VM, and we update the secondary. And by doing that, we preserve state and ensure globally consistent state.
Thank you very much, Ali.
You're welcome, Michael.
Excellent. Great presentation.